In this video, we're going to talk about how to take the derivative implicitly. So let's talk about what that means. If we have a function that's written explicitly, that means it's written as y equals something. So we can think about it. These are actually functions because y is just a fancy way of saying f of x. When it's something that is written implicitly, that means it's not solved for y. So this equation of a circle centered at 0, 0 with radius 5 would be a good example of something that's written implicitly. It's not solved for y. Even if we had a line like 5x minus 2y is equal to 15, that would be written implicitly because it's not solved for y. Now, in this case, this is a function, whereas this is not a function. Implicit doesn't mean it's a function or it's not a function. It just means it's not solved for y. Some of them will be functions, some won't be. So then how do we take the derivative? We take the derivative the way that we always do. We just have to remember that anytime we take the derivative of a variable that's not x, then we need to show we took that derivative with respect to x. So let's look at what's happening with this first one. We have x squared plus y squared is equal to 25, and we want to take the derivative of the function. So if I take the derivative of x squared, I'm going to get 2x. So technically what's going on is we need to show we took the derivative of the function of the variable x with respect to x. But dx over dx is the same thing as 1, so we don't normally write that. When I do the derivative with respect to y, I'm going to do the same thing. I'm going to show that I took that derivative with respect to y. And that's going to be equal to the derivative of 25, which is 0. So we're going to take the derivative on both sides of the equation, and we're going to take the derivative of every term. So now we have 2x plus 2y, and I typically write this as a y prime, and that's going to be equal to 0. Now the goal is always to solve for y prime. And you're always going to be able to solve for y prime. So to do that in this case, we're going to move that 2x to the other side, and then we're going to divide by 2y. I'm going to get negative x over y. So this would give me the slope of the tangent line anywhere around that circle. So let's add a part b to this. Let's say we want to find the slope of the tangent line at the point x equals square root of 5. So we're going to need to find y values. So we know x squared plus y squared is equal to 25. If I plug my x in, I can solve for y. So y is going to be plus or minus square root of 20. Remember, 20 is the same thing as 4 times 5. So this is really plus or minus 2 square root of 5. So here's what's going on with this problem. We have the circle x squared plus y squared equals 25, which is a circle that's centered at 0, 0 with a radius of 5. Square root of 5, if we were to get a decimal approximation for that, is about 2.24. So 5, 2.24. That would be slopes here and here. That's why we end up with two values. When I take the square root, I always have a plus or minus, but we're going to have two values. One's going to be a positive and the other one's going to be a negative. So we have 2 points we're looking at. We're looking at the point x equals square root of 5, y equals 2 square root of 5, and then we're looking at the point x equals square root of 5, y equals negative 2 square root of 5. So let's find the slope of those tangent lines. So we know the slope's going to come from that derivative. So y prime, and I'm going to show I'm plugging this point in. I'm going to do a little subscript here with just that point in it. My derivative is negative x over y. You see how their square root of 5s are canceling, so my slope here at this point would be negative 1/2. And then when I plug in that other point, which is square root of 5, negative 2 square root of 5, I'm plugging in the negative of x over y. And you can see how the square roots are going to cancel and the negatives are going to cancel, and that's going to give me a positive slope here. So I'm looking at this point, and you can see how that's going to be a positive slope.